Hello kids, welcome back to Algebra 1 with Miss Betsy. We are continuing our work with solving simultaneous equations or solving systems of linear equations. We're just at the very beginning of this, so we're only dealing with two equations, and we're still discussing exactly how two lines can interact in a plane. Now I'm using as my text Algebra 1 for Christian schools. It's published by Bob Jones University Press. I'm using the second edition. If you're tracking with me, I am on page 276, section 7.2, using the graphing method. You don't have to use that text. It's the same material everywhere. Now I've got an ultra lame joke before that I'm sure you've heard, but I'm running out of jokes. I've got to go to the library and get some new ones. What did the duck say to the comedian? Oh man, you quack me up. So, as I told you, they're really lame today. So we've been discussing that it's possible to find a solution to a system of equations on a graph if you have two lines that intersect. How many solutions are there right here? Well, there's one solution. Only one point where those lines intersect. Okay? Only one point where you can have the same answer for both of these. So you have two lines that can cross. What's another way that two lines could interact with one another as long as those lines were in the same plane? How else could they relate? Well, think about railroad tracks. You can have two lines that are parallel to one another, and they're never going to touch, are there? Not ever going to be a solution to those because they're different. What's another way that lines could relate to one another? Well, what if we had this red line here that represents the graph of an equation? And what if somebody comes in and says, no, I don't like that red. I think I'm going to put blue down right on top of it. That's right. These lines, this is what they call collinear lines. Lines that are exactly the same. The same equation represents the same line. These are collinear. So you can have three different ways that lines can interact. They can be collinear, they can be parallel, and they can be intersecting. There's also a relationship between two lines, and these are called skew lines, but skew lines are not in the same plane. It's like here's the plane and maybe an arrow going through the board, like through this line here. Those two lines would intersect, but they would be called skew lines because the line is not in the same flat surface here. So getting back to just being what we can graph in a plane, there are only three ways that those lines can intersect. They can be three ways that those lines can relate to one another. They can be intersecting, they can be parallel, or they can be collinear. Now let's look at these and see how many solutions, how many points are going to fulfill both of these equations. Well, obviously there's only one. There's one solution, and it's that one point in the plane where those two lines cross. With parallel lines, how many solutions are there? How many times are they going to touch? Well, we've got a problem if our railroad track comes together and touches. Parallel lines continue infinitely in either direction, and they never intersect. So there's no solution to these. And what about collinear lines? Well, collinear lines are the ones that lie right on top of each other. So it's, you put Here's one line, here's another line, they're sitting right on top of each other. There's an infinite number of places of intersection where those lines touch. So there are infinite solutions if the lines are collinear. Now we have some new vocabulary here, and this is when we talk about consistent and inconsistent systems. Okay, what are consistent systems? Well, consistent systems have at least one solution. Let me say right here. Consistent systems have at least one solution. What's the opposite of consistent here? That would be inconsistent. So if consistent systems have at least one solution, inconsistent systems have no solutions. So let's look back up here. What do we have? Is there at least one solution here? Yes. So this is a consistent system. Is there at least one solution at one point of intersection with the parallel lines? No. There's no point of where they're touching, so this is an inconsistent system because there are no solutions. Inconsistent. What about our collinear system right here? Is there at least one solution? Well, yeah, not only is there one, but there's an infinite number of solutions. But in order for it to be consistent, it only requires at least one. So collinear systems are also consistent. Now, there's another definition that we need to have, and we're talking about dependent systems. And we're going to have dependent and independent. A dependent system of equations has an infinite number of solutions. We have an infinite number of solutions, so this is dependent. Collinear lines have an infinite number of solutions. They are consistent, meaning that they have at least one solution, and they are dependent, meaning that they have, as your book says, meaning that they have an infinite number of solutions. So dependent and infinite mean the same thing. You know, we have an infinite number of solutions, so they're dependent. What about parallel? They're not dependent, they don't have any solution. So parallel lines are simply inconsistent, and they have no solution. Now, finally, we have intersecting lines. They have one solution. They are consistent. They are not dependent, so they are independent. These ways of classifying and separating systems of equation, consistent, independent, inconsistent, consistent, dependent, you're going to have to sit down and figure out some way that you can get these all straight in your head, because they will ask you, they will expect you to know that consistent means that there's a solution. Independent means that they only intersect at one point. If a system of equations is consistent and independent, you know they have to be intersecting lines. If they tell you that a system of equations is inconsistent, you need to know that that means there's no point of intersection in those two lines, that they never touch, which means that those two lines have to be parallel. There's no other way that they can relate to one another. Finally, if they tell you that a system of equations is both consistent and dependent, that tells you, first off, not only is there a solution to a point of intersection to those lines, but it also tells you that they are dependent, which means that there is an infinite number of solutions, which means that those two lines are lying right on top of one another, and they are collinear. You need to spend whatever time you need to understand these definitions and to be able to play with them. It took me even a while to get all of the vocabulary twisted and turned around, because it's different than what we do in real life. But you have to know this. Lines can relate to one another in a plane in only one of three ways. They can intersect, at which point they have one point of intersection. They're independent because they have one solution. They're consistent because they have at least one. Lines can be parallel. There's no point where those two lines touch, so they are inconsistent. There is no solution. And finally, you can have the lines that lie one right on top of another because there is a solution. They're called consistent because they touch every place. They meet everywhere. There are an infinite number of solutions. They're called dependent. Okay, so now let's go ahead and look at a few graphs. I'm going to go ahead and solve this system of equations. X plus y is 3. X plus y is 7. X plus y is 3, and I'm going to change this to x plus y is 1. The picture is going to be the same. It's just going to make it easier for me to graph, because I'm noticing that once again I don't have my graph marked. 1, 2, 3, 4, 1, 2, 3, 4, -1, -2, -2, -3, -4. What do I need to do here? I need to put both of these equations in slope-intercept form. Y is equal to -x plus 3. Y is equal to -x plus 1. Now, what do you notice about these two lines? They both have exactly the same slope, don't they? But they intersect the y-axis at different points. My red line, the y-intercept is a point 3, has a slope of -1. And I left my straight edge way over here. This is a very nice, easy equation to graph. I'm only going to label the line itself, -x plus y is 3. Now if it has a slope of -1, it's down 1 over 1. So what's that going to mean? Every line that has a slope of a -1 is going to be parallel to that. Well, let's see what happens. Our second equation says y is equal to -x plus 1. Here's my y-intercept, down 1 over 1. Draw a straight line connecting those 2 points. Sure enough, we have 2 parallel lines. So what you can learn from this, what you pull from this, is if 2 lines have the same slope, both have to be negative or both have to be positive, they're going to be parallel. And if they're parallel, what's the solution? There is no solution. Because when you solve a system of equations, what you are looking for is the point at which those two lines cross one another or lie right on top of one another, in which case they're collinear. So there's no solution. These are parallel lines and they are inconsistent. So now let's go ahead and look what our next one is. We have 2x plus y is negative 4. (2x plus y is a negative 4. And we also have x minus 3y is a negative 9. And I don't want to do that. Do I want, yeah. X minus 3y is a negative 9. X minus 3y is a negative 9. What do we need to do to solve this system of equations? To illustrate it graphically, we'll go ahead and solve both equations for y, which will put this into the slope-intercept form of a line. Negative 3y is negative x minus 9. Now we're going to divide both sides of the equation by 3 by negative 3. We have negative 3y divided by negative 3 is equal to negative x divided by negative 3 minus 9 divided by negative 3. I'm going to go ahead and put that in brackets here. So that I don't drop the negative. See, I have minus a negative. Negative divided by negative is a positive. Y is equal to 1/3 x plus 3. We now have the slope-intercept form of a line. The y-intercept is a point where y is equal to 3. 1, 2, 3. We have a slope of 1/3. It's a gentle slope. 1, 2, 3. From here we're going to go down 1 and over 3 to give us our second point on the line. Let's go ahead and connect these. Minus 3y is negative 9. Now we need to take our second equation here and let's go ahead and put that in slope-intercept form of a line. What do we have? We have y is equal to negative 2x minus 4. So we have a negative, we have a negative slope here. Now look at this. Said we have a positive 1/3 slope. I graphed it with a negative 1/3, didn't I? Good thing I have a spare graph over here. I'm not going to redo this video. 1, 2, 3. 1, 2, 3. We have a y-intercept of 3. We have a slope of a positive 1/3, up 1, 1, 2, 3, over 3. All the difference in the world here. This is the graph of our first equation that we solved. X minus 3y is negative 9. X minus 3y is a negative 9. Now, 2x plus y is a negative 4. Let me go ahead and switch back to my red marker on this. Y is equal to negative 2x minus 4. I want to find my y-intercept. Negative 1, negative 2, negative 3, negative 4. Right there's my y-intercept. What is my slope? It's a -2. Can move up 2 and over 1. Connect these two dots. And notwithstanding the point that I have some writing here, we see that this system of equations here does have a solution. The solution, this is where x is 1, 2, 3, -3, and y is 2. So these two lines right here, they're intersecting, which means they intersect at one point. Our solution is a -3 and a 2, where x is -3, y is 2. The system of equations right here, this original system of equations, the 2x plus y is a -4. The x minus 3y is a -9. This original system of equations right here is consistent because there's at least one solution. It is independent because there is only one point of intersection, and therefore we know that these two lines are simply intersecting in one point. So now we've seen parallel lines, we've seen intersecting lines. Now let's see what our collinear lines are going to look like. X plus y is 3, 2x plus 2y is 6. X plus y is 3, 2x plus 2y is 6. What are we going to do? We're going to graph both equations on the same line. This one in slope-intercept form, y is equal to -x plus 3. Graph this, the y-intercept is a +3, slope of -1. See what happens here. 2x, let me use a different color marker. (2x plus 2y is equal to 6. We're going to put this into slope-intercept form of the line. 2y minus 2x. 2y is equal to a -2x plus 6. I subtracted both sides from both sides of the equation, the 2x. We have to divide both sides of this equation by 2. But would you look at this? Y is equal to a -x plus 3. This is very, very key. When we put both of these equations right here into slope-intercept form, look at this, we get the very same thing. Y is equal to -x plus 3. Y is equal to -x plus 3. You can recognize these collinear lines by the fact that there is a, see how this is multiplied? If you take this whole equation, you multiply the left-hand side by 2, the right-hand side by 2, you end up with this equation. So these right here, y is equal to -x plus 3. 1, 2, 3, and 1. Y-intercept right here is y, -1 slope. Here's the first equation. And then the second equation simply lies down right on top of it. because you have 3 and a slope of -1. So what we've illustrated for you today are the 3 relationships that are possible between 2 lines in a plane. They can be parallel. If they're parallel, there is no intersection. There's no point where both lines have the same solution. So there's no solution to that system of equations, and we say that the lines are inconsistent. There is no solution. We can also have those 2 lines simply be intersecting lines. There's one point of intersection. We would say that they're consistent because there is a solution. We say they are independent because there's only one solution. And then finally we have our last way in which 2 lines can interact in the plane, where where both of the equations represent the same line. So they are called collinear. They are consistent because there is a solution. They are dependent because there are an infinite number of solutions. That's what section 7.2 is about, primarily about understanding how those two lines can interact with one another in a plane, and consistent, dependent, independent, collinear, just a bunch of vocabulary. Make sure you learn that, and I'll see you next time.